This is an introduction and demonstration of the full chip pattern integration solution from TSSI. Full chip pattern integration refers to those designs that have multiple test pattern sets that will need to be conditioned and combined. This commonly occurs with designs that have multiple IP blocks. It's usually necessary to route test pins to the chip level. Test patterns will need to be merged to execute sequentially or concurrently. To meet the challenges of full chip pattern integration, we need a generalized approach that can be applied to a wide variety of designs, regardless of size and complexity. We'll need to handle large test files from various sources. Our process must be robust to minimize errors and to be able to execute interactively or in batch. Our goal is a generalized approach to test file merging so it can be applied to all levels of design complexity. This diagram has an x-axis representing the number of chip-level pins. This is an important factor when scheduling tests of individual IP. The y-axis represents total test time. Before each test, a setup sequence is executed, so pins are routed to the chip level and other setup operations are performed, such as clock and power domain selection. Almost all test pattern files require some type of manipulation prior to targeting a tester. One of the most common approaches is to execute a Perl script that manipulates an ASCII test pattern file, such as one in style format. Besides being very time-consuming, this approach creates a process that is error-prone and cannot be easily adapted to different designs. The TSSI full chip pattern integration approach utilizes a database. The input test files are converted into the waveform database. This makes data manipulations easier and minimizes errors. The test data is more easily visualized with graphical tools instead of using a text editor such as Vi or Emacs. Our generalized approach to full chip pattern integration needs to be versatile. Therefore, we need a full set of elemental capabilities that can be used in various combinations. Here is a partial list of some of the operations available within TDS that can be applied. Specifications for the operations are simple, using tabular lists. Now it's time to show a demonstration of full chip pattern integration using TDS. For this demo, we start with a test pattern file for an ARM core. The test file is style format, representing a scan test generated at the core level by Tetramax ATPG from Synopsys. We will prepare the test for chip level operation. This includes deleting signals that don't go to the chip level and adding some signals to support test access of the core. Signals will need to be renamed to match chip level. Some need to be changed to bidirectional, and a couple need to be inverted. A preamble is created and added to the front of the test file. After the test file is ready for chip-level access, it will be converted to an Advantest T2000 test file. Finally, a set of virtual test models are created for Verilog simulation. This includes Verilog models of the test program and the T2000 tester. We start the demonstration in the TDS WaveMaker environment. There are two major aspects of the TDS that make it different than other test conversion methods. First, the interactive flow environment that we see here. You can quickly create a flow that will perform the operations to convert your test files. Once the flow is captured, it can be run interactively or executed as a batch command. Many users find it most expedient to simply copy an existing flow and modify it accordingly. The second unique aspect of TDS is the waveform database for representing the test data. As we can see, the first operation performed in this flow converts the style file to a waveform database. Once in the database format, we perform various operations on the test data. After each operation, the data is held in a new database. This makes it easy to track modifications throughout the process. One of the advantages of holding the test data in a database instead of an ASCII file such as style is that we get the ability to easily view and edit the data. For example, we'll invoke the signal definition editor on this database. We can easily view the signal list and each signal's attributes. There are many features to this editor. Not only can you view the signals, but you can easily change any of the signal attributes. Another useful tool for looking at the data is the pattern editor. The signals are shown across the top. The patterns are listed sequentially, along with the time, cycle, template, etc. As noted earlier, this is a test file for a scan test. We can also see this by the symbol representing a scan unload and the change in the cycle count. Like the signal editor, manual changes can be made to the patterns. We can also look at the time plates with the timing editor. This represents a graphical view of what's in the timing section. We can see the timing is specified for each of the time plates. And again, we can manually make changes if we wish. The waveform editor is a great tool to see how things will look on the tester. It combines the information from the patterns and the timing to give you a rendering of the signal waveforms. Now let's go back to the desktop and step through the flow. The first operation is to convert the core level style file to a waveform database. This conversion makes it easy to perform other data manipulations without resorting to editing ASCII files with scripts. You may recall that our core level test file has 3,000 internal signals. Only 81 of these signals will be brought to the chip level. The rest should be deleted along with any other pattern data associated with them. We decided to perform this operation first, so to shrink the size of the data file. We could have decided to specify each of the 2,920 signals that are to be deleted. However, we find it more expedient to simply list out the 81 signals that we wish to keep. They are specified in a simple spreadsheet format and output as a tab-separated list. The tab-separated list of values is shown here as an input to the signal edit conditioner. The resultant test data is put into this waveform database. The next signal edit conditioner performs 4 different types of operations at once. The first operations add in some new signals. These new signals will be used to control the test access mechanism, or TAM. The next operations change some of the signals to bidirectional. Next, we rename all the signals so that they are set to the proper chip level name. Finally, we invert 2 of the signals. Again, we save the file as a tab-separated list. As you can see, these manipulations are just a matter of listing out simple tables of values. Here again, we see the tab-separated value list for controlling this signal edit conditioner. The resultant test data is put into this waveform database. Now the test file is ready for the chip level. Now we are ready to prepend a preamble test sequence to the test file. This preamble will set up the IP core for testing, such as directing the signals to the chip level, selecting clocks, power supplies, resets, etc. The preamble file can be created any number of ways. It can be generated directly from simulation results, reading an EBCD file. It can be created by directly editing a TDS waveform database. Or it can be done as we have here. We input another style file. Here it is converted to a waveform database. The WDB conditioner is capable of many functions. In this case, we have chosen for it to perform a concatenate function to attach the preamble waveform database to the main test waveform database. We now have the chip level WDB ready to target an ATE with a bridge. Note that throughout this process we have been dealing only with waveform databases. This makes the whole process easier, simpler, and more robust. There is never a need to edit ASCII files with scripts. However, it is always possible to get back to a style file if you wish, by simply using a style out converter on the waveform database. Here we show you how it can be added to the flow and be performed automatically. Now we are ready to convert the waveform database to a set of tester files. For this example, we chose the Adventist T2000. All the files are placed in this directory. The final stage we have chosen for this demo is to compile the T2000 test program into a Verilog model. This compiler will create a virtual model for the T2000 and ready for executing a simulation with the test program in the DUT. TSSI actually offers several levels of verification modeling, including running a simulation of the patterns accessing the waveform database directly. To execute this scenario, select the Run pull-down. You can choose to run the entire scenario, or you can execute a selected subset of operations. Of course, once the scenario is set up, you can run it in batch directly from a command line. The TSSI toolset has a rich set of functionality, and we have only touched on a few of the capabilities in this demonstration. If you would like to see a more in-depth demo, please contact us by email or phone.